It's March the 6th. All right, I actually have some idea about this. I didn't thought about, well, I tried to think about it before I went to bed, before I fell asleep, but didn't come up with anything. But today, while I was warming up for Snatch, I just suddenly, oh my God, what did I do? I just suddenly realized that maybe, just maybe, I can use something called, what's that? Monotonic stack to solve this. Because if you think of a monotonic stack, what is a monotonic stack? Right? It's constantly going up. So between each element, pair of element in the monotonic stack, everything inside is smaller than them. Right? So maybe there is something that we can do to count how many quadruplets is bounded by these two, right? Maybe it's possible. Maybe it's not. I'm not sure. I'm not sure, but we'll see. Maybe it'll work. Maybe. But let's do this first. Looks to be a difficult one because only 35% passing rate. Minimum time to complete trips. Have I done this? 2,100, maybe not. You're given array time, and the times I denotes the time taken for the ith bus to complete one trip. Each bus can make multiple trips successively. That is, the next trip can start immediately after completing the current trip. Also, each bus operates independently. That is, the trips of one bus do not influence the trips of the other bus. Okay. You're also given an integer, total trips, which denotes the number of trips all buses should take in total. Return the minimum time required for all buses to complete at least total trips. Okay. The minimum time required for all buses to complete at least total trips. So time 1, number of trips completed by each bus are. At time 2, the number of trips completed is. At time 3, the minimum time for all the buses to complete. Hold a second. Let me do this one more time. You're given an array where a time I denotes the time taken for the ith bus. Okay. Each bus can make multiple trips successively. Okay. The next trip can start immediately after the completing the current trip. Okay. Each bus independently. Okay. You're also given a number of total trips. So what we're looking for is to find the minimum number of time to do 5 trips. So I say 3 time. So for 3 time, the first bus goes 3 times. The second bus goes 1 time. And the third bus goes 1 time. So in total is 5 trips. And the second one, total trips is 1, so it requires 2. Right? Only 1 bus. Okay, so we want to know the minimum time. The minimum time. So everybody should go in parallel, right? Because that's always the best strategy. So basically this is asking if all the buses are going parallel, what's the minimum number of time needed to complete the total trips, number of trips. Now we can sort everything from small to large, right? And we can say time point something. Binary search. So I have the time, right? So we basically saying, given me a time, and I want to see how many trips can we do in this time. So if I sort time and it give me a time, then everything smaller can be computed. We can just do div mod, not div mod, just divide until we cannot. So that's on, and that's on log n, right? Okay, what's the minimum? Well, minimum is going to be 1, so our start is 0. What's the maximum? Well, maximum amount of time will be trips. Well, maximum is going to be the largest value in time times total trips plus 1. That will be the maximum. So that's how I'm going to start. And we will see how this one goes. So first of all, we need to sort this, and the low shall equal to 0, right? High, say time minus 1 times total trips plus 1. Okay, while low is smaller than high, mid is low plus high divided by 2, right? Then we say trips, right, equals 0, and for t in time, right, if t is larger than mid, then we'll break. Otherwise, we say trips plus equal to mid is the time divided by t is how many trips. So once we're done, we say if trips, okay, make more trips, right? If we make more trips, then we shall decrease the time, so we have too much time, right? So, okay, so we say high equals mid, right? Else, if we have trips is smaller or equal to, then we shall increase. Wait, what we want? We want the minimum time, right? We want a minimum time. So if the number of trips is too much, so we need to bring it down. If the number of trips is, maybe the trips is larger or equal to, then we shall bring it down. If the trips number is smaller than total trips, then we need to bring it up. Yeah, if the trips number is smaller, then we say low equals mid plus 1. And we can return, what do we return? So trips are larger than, and we can do this. Trips are smaller or equal to, then we try go up. So what's going to happen is, if it's equal to total trips, now I'll try to get low, or try to get higher, and that doesn't make any sense. Why would you want the time to get bigger? You want a minimum time, right? You want the minimum time. Required. So why don't we say if trips is larger or equal to, then we bring high to mid. How about this? Trips is larger or equal to. So if it's equal to, we try to move low as well. If it's smaller, that means it's definitely not good, so we're gonna bring up. So in this case, I think I might just return low. Okay, let's give this a shot. So this one should be 3. This one should be 2. Man, it's been raining the whole day. Not the whole day, but a large part of the day. All right, so now all we need to do is to check. Say time length can be 1, right? Ooh, what if 2 total trips 10? We just need to do it a lot of times. What if I have, I don't know, I'm just randomly doing this. Looks promising. Give it a shot. Oh, I did this before. Okay, so I bet the solution was the same. What was the previous solution? Sort this, trip, and break larger. Yep, that's exactly the same. I thought it'd be faster doing this way. When was the last time I do this? About a year ago. Let me search. N. It's not technically N because it's this. Oh, it is N. Log. M times K. Right, where M is the largest of time and K is total trips. Okay, so this one's done. We have some time left, so I want to explore, you know, a monotonic increasing. Does that work? So we have 1, 3, right? 2 put in there. 4 comes in. So 4 can pop 2 out, right? 4 can pop 2 out. So now it's 4, right? And 4, and then 5, right? That's the monotonic. And then what? We had to look at 5 and 4. 5 and 4, there's nothing. 5 and 3. 5 and 3. 5 and 3. They have to be 5 and 3, right? So something is. Hold on. What we're trying to say is all these are kind of like, you know, peaks, right? Then we try and find out if there exists. So we say 4 and 5. It does not exist. There's nothing in there, right? 3 and 4. 3 and 4. Nothing exists because of the value in between. We have a value which is smaller than both, right? Which is smaller than both. So we have one value smaller than both in between. But 3 and 4 we have nothing. 1 and 3 we have nothing. Okay. So now we do 3 and 5. So 3 and 5 we have. This is smaller. 3 and 5, we have one smaller in between 3 and 5. Then how do we compute? So we shall know in 3 and 5, we have one value, but in actual we have two values, so we have one value that's smaller. So with that, 3 and 5, we can form a valley, right? We can form a valley. So anything to the left can use 3 to 5, right? So for 1, so 1 is good. So we have 1. So we find number of valleys. So 3 and 5. Yeah, because we start 5 and 4. Oh, we can do 5 and 4. Right, nothing. And 5 and 3, we have 1. 5, we can now do 5 and 1. Because 5 and 1, we don't have anything on the left. So that's 1. Okay, now we do 4 and 3. 4 and 3, we have 1 in between. So we have 1. So that's why it's 2. I think it is monotonic array. So we do monotonic array. Then for each, so after we do the monotonic array, for each adjacent, okay, for each adjacent, we can find how many is in between. That is a given, right? We will know how many is in between. Okay, so we know how many is in between. And then, all right. So we know how many is in between. Yep, we know how many is in between, and then just multiply by how many on the left side. How many is in this? Multiply on the left side. How many is in this? Multiply on the left side. That's O(n) squared. That is O(n) squared, but I am willing to give this a shot. Okay? Let's give this a shot. Gotta be bold. Gotta try it out. Give it a shot. So what we do is stack, right? Monotonic stack. We'll put num0 in it. Oh, actually that's not true. That's not true. How about the first one? We need something that's smaller. We have something big. What are we gonna do? Yeah, we have something that's big in here. Then we have something bigger later on. Oh, you know what? I don't think so. I don't think so. Because they could be additional, additional inside. You see what I'm saying? It could be additional inside. Like if the star is super big, right? And then we have another super big. Okay, so we have 2 super big, and then within this boundary of super big, we have a bunch of others. And they can form their own thing. But they will all be eliminated by the outside. Jesus. Okay, are you saying what I think you're saying? We will focus on every single one. We locate the first one. So we'll do a monotonic stack, right? And then we say we want to find all the quadruplets with num0 as the starting point. and then we can do one run. Okay, do a run every time we find something that's bigger than it, right? That's bigger than it, and we count how many is in between. That's bigger than it, and then we count how many is in between. Can we say like we eliminate these? Oh, it doesn't gonna work. It doesn't save time. Okay, so let's say we go to the end. All right, so and then what do we want to do? We want to find out, starting with the first one, and we have this. Because in between it has to be higher, right? Which means we need to have at least, we need to have 3 peaks. All right, we need to have 3 peaks. Yeah, we need to have 3 peaks. I smaller than num k, smaller than num j, so what we're looking at is IJL, right? IJL. So we're looking at IJL. We're looking at IJL. Then we just need to know how many is it between J and L, right? How many is between J and L? Therefore, what we're looking for is, we have the first, right? We have the first one, and then the second one is slightly higher. They don't really care about how many is in between these two. And then we got a third one, okay? So when we get this one, we can calculate how many is in between this. That will be the first, right? That will be the first. And then we have the fourth one. Then we can calculate how much is in between these. Then we have another one. And we can calculate how many in between these two, right? And we got another one. So it's how many in this, how many in this, and how many in this. So what we're saying is, if this is, let's say, A1, these A2, these A3, what we're looking for is, the first one is A1, second one is A2, right? Because we use these two, and now we can use these two, so that's A2 plus A1 plus A2. And the third one will be A3 plus, we use these two, will be A2 plus A3. We use these three is A1 plus A2 plus A3. That's the total numbers starting from the first one. So if we summarize this is A1 plus A2 plus A2, A1 plus A2 plus A3, plus A2 plus A3 plus A3. So what is this? So if we add them together, that's 3A1 plus A1, 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 A2, 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 A3, A3, A2, 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 A1, 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 and then we have A2, 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 1, 2, 3, 4 times A2, and then A3, 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 3 times A3. That's not some rules that I can find. You gotta figure it out, man. Hold on. Let me do it one more time. One more time. What we're looking at is A1, right? Second one, we need A1 plus A2, and we'll plus A2. Third one is A1 plus A2 plus A3, and then A2 plus A3, and then A3. Fourth one is A1, A2, A3, A4, A2, A3, A4, A3, A4, A4. And each one of them are different, right? Because the first one is this. How's this? We add this, so we can go this, right? Go ahead and this. Yes. Each one's different. So we want to add them together and try to find out if there's any rules in it. What are the rules in it? Because that's just starting from A1. Starting from this first one. We also need to find the second one and the third one. So this has to be ON. We have to figure out a way to compute this in ON. Then how do we compute this in ON? This is all the A1s. A2, A3, A4. So it's 4 A1, 3 A2, 2 A3, and an A4. And then we have 3 A2, 3 A2, 2 A3, and A4. And we have 2 A3, A4, and A4. What does this give us? 4 A1, 6 A2, 6 A3, 4 A4. 1664. What was that? Yeah, that's binary extension. It's binary thing. It's the Pascal triangle. Now, Pascal triangle can be extended, but each one will be multiplied by how do we find these values quickly? What do we want? We want their coefficient. How can we get a coefficient? How can we get their coefficient? I mean, we know how many there will be. Oh, the value doesn't get huge. I cannot do it that way. It's gonna be so slow. try it again. If this one we have A1, right? And then we can say S plus whatever we have in the previous. It's going to be this plus this. So whatever we have previous plus A2. And then plus A2. So that's A1 plus not really. So the first one's A1, right? The second one we need to plus A1 plus A2 plus A2. That's actually 2A1 plus 2A2. Yeah. So 1, 2, 2. No, 2, 2. 1, 2. 1, 2, 2. Should be 1, 2, 1, right? So S equals this. Now A3 comes in. A3 comes in. So we're going to add A3. And then whatever previous we have, we need to double it. Because let's say if we have this much, okay, in the previous, in total, yeah, as we reach 0, we have in the total, right, in total, all that we have, and all of them can be matched. So shouldn't that just be, so S equal A1, then S equal to S plus A2. Right? Well, plus A2 by itself. And it will plus, so 2 times this plus A2. So that will be 2A1 plus 2A2. So the next one will be 4A1 plus 4A2 plus A3. Plus 3A3. 3A3. So we can, this fit this, right? This by itself, this fit this, and this fit this. It's the total we have, right? So we're ending at here. Start from here, ending at here. Start from here, ending at here. What we have is the total. Total. Then what we say is this total can all fit with this. Every single one of them. can fit with A3, right? Every single one of them. It's not really every single one of them. We say this is going to be A3. We say this is going to be this. We say this is going to be this. Which means if I have a, because now we have this plus this, right? We have this, we have this, right? We have an A2, and we have A1 plus A2, right? And now we have A3 comes in. So when I need this one to be A3 plus A2, is A1 plus A2 plus A3. Hold on. We'll do it one more time. If I have A4, A3, A2, A1, prefix sum, right? That's the prefix sum. And all of this added together, this is, okay, with all of this added together. Now, to figure out this part, is all of this added together, A3 plus A2 plus A3. So all this added together. So we need to do this sum and this sum, right? So if I do a prefix sum of a prefix sum, you heard what you're saying? Did you hear what you're saying? I did hear what I did, and I know it's crazy. So, but anyway, total sum, right? And then this total sum we can calculate. Because we have the prefix sum of this prefix sum, then this we can calculate. And once this is calculated, right? Once this is calculated, we just need to minus this and multiply by A4. And then we do this is calculated. We minus this multiplied by A4 and multiplied by A3. Then we have A2 plus hold on. A2 plus A2 and A1. And here is just all these. So we have multiple, dear Lord. And that's just for one. But all of them will be the same. So that's okay. That's actually okay. So it will be O(n) squared. Now we are computing things that's, So what are you saying? We do that. And every time we find something, we push it. No, we don't push it in. We get the stack, then we go from right to left, push the value in. Okay? And then we form up that. And then we do the prefix sum of the prefix sum. Then we do this, and we do the second one. Right, so prefix sum of the prefix sum is You know, this plus, yeah, this minus this minus this. And then we need to know, okay, what you're suggesting is, okay, and stack, right? And then we do for j in range I plus 1 all the way to n. Okay. Now what? Range 1, we say while stack. No, we don't pop n. N has to stay there. While so if this is bigger, if this one is bigger, then we just pop until we find something that's smaller, right? Until we find something smaller. So if something is smaller, then you just pop until you find something smaller. That doesn't make any sense. So if something is bigger than you just pan, bigger than your pan. If it's smaller, then just pop. But what if I have something that's super high? Yeah, what if you have something super high? Small? If it's larger? No, that's the monotonic decreasing. What's the monotonic increasing? Increasing if it is something small. Then if something is this, then we'll pop. Yeah. So something, if it's larger, if the top of the stack is larger than me, then we'll pop. Okay. So top of the stack is larger than me, we'll pop. So if it's small, if it's larger than me, then we will pop. You sure? You sure it's gonna pop? You know what? I don't know. If you pop a big one, right? Say if it's something that's larger than me, now I pop it. Yeah, you cannot pop something that's larger than me. Then everything pop is something larger than you. But hold on. But the ideal is okay. So, but maybe we shouldn't call it the stack. The ideal is to find everything that's larger than me. All right. Okay. If we find that anything that's larger than me, and if it's larger than me, then we put it in. If it's larger than me, then I put it in. So I have a bunch of things that's larger than me. But what I want is an increasing thing. Okay? It's the increasing thing. Which means I need to know which ones form an increasing. So I have this, right? And an increasing subsequence. We want to find an increasing subsequence. But there will be so many. There will be so many increasing subsequence. Well, I thought I had an idea. This one that works, but I need to find an increasing subsequence. But the question is, how do we find an increasing subsequence? A monotonic increasing does not work, because a monotonic, the things you pop is things bigger than you. Right? You find something bigger than you append, and you find something it's bigger than you, then you want to pop. Right? The things you pop is bigger than you. The things you pop is bigger than you. Things you pop is bigger than you. It doesn't work. It doesn't work. I mean, given a number, right? Given any number, I know who is bigger than me. I know. I know. I just need to know towards my right. Towards my right. Smaller than me, I don't care. If something bigger than me, I mark it. Right? Another one bigger than me. So all these are bigger than me. Okay. Then what do you want? Among those bigger than me, I want to find a pair. I want to find a pair that's bigger than me and also increasing. Or you can say, I want to find in between these two, okay, between these two, how many are in between? Larger than this and smaller than this. Okay, so we start with this, then we get a whole number. Okay, and then we want to know among this, how many are bigger than this? Well, all of them are bigger than this, right? So how many are smaller than that? Than the end? So for this, we can go through to see how many are smaller. And for each that is smaller, we can find the total number smaller inside. Smaller inside. Okay, this might work, but it's gonna be O(n)² just for one of them. Ah, dang it. I think I have to look at a hint. All right, but not today. I'll see you guys tomorrow. Adios. Didn't work.